Cool. Yeah, so this was originally a presentation that my colleague Pedro and I gave at KubeCon EU earlier this year, and excited to be presenting it again because it's sort of the redemption round. The demo gods did not play ball, and maybe this is lame, but I'm going to be showing a recorded demo today, so we know it's going to work. At least that'll be hopefully interesting for everyone. But yeah, I'm Tyler Gillson, Principal Software Engineer at Spectro Cloud. And this two-node project is kind of my baby that I've worked on for the last while, and hopefully it can start saving some cost in production. And it's also just cool technically, at least I thought. Okay, so yeah, that's me. Feel free to reach out on LinkedIn or GitHub, and I'll just get into it. So imagine you are someone who owns a big chain of gas stations, or maybe you're a retailer, or anyone who's owning and operating a business that involves hundreds or possibly thousands of edge locations. A lot of the time these days in situations like that, we're seeing more and more real-time inferencing, and we have production applications that are contributing directly to the bottom line, and we can't tolerate downtime. So if we know that every minute that one of these apps is offline, we're losing money, then obviously we want some level of redundancy. So in Kubernetes world, as we know it, that means we need high availability, which means we need at least 3 nodes. Basically, this is a given because of etcd. So I'm sure most people here are familiar with etcd, but basically it's the key value store that serves as the quote unquote brain for Kubernetes. Okay, I just was looking at the chat for a second, sorry. So feel free to interrupt me also if you have questions. But yeah, so etcd is where we store all of the resources that we are manipulating within Kubernetes API server, and it's highly, in order for it to be highly available, we need an odd number of nodes due to the fact that it uses the Raft algorithm to establish consensus, and Raft requires a quorum. So in the picture here, we can blame it on etcd, but just to be clear, this is a fantastic piece of technology, and it makes a lot of sense to do things this way. It's only in this niche use case where we're really concerned about cutting down on all these costs, because when you think about having 3 nodes, it's triplication for not only the hardware, but also the cabling, and even space. Like at some of these edge locations, we're constrained physically, and you might have to pay for a larger physical container to put these 3 boxes in. So when we're thinking about operating at scale, thousands of locations, and that's where it starts to really get painful, and where doing something crazy like using 2 nodes begins to make sense. Maybe, you tell me. But anyway, it's etcd's fault. So there are some alternatives, and here's why they don't measure up. Basically, if you want to use a single node, that's too risky. Some applications, some use cases can get away with that if it's a weather station and you're fine with downtime. But like I mentioned before, if it's going to impact your bottom line, you just can't do that. And then you might ask, okay, why not do 2 node with etcd? And the problem there is that when you lose a node, you enter a degraded state, and there's basically just absolutely no benefit to doing this. All you're doing is paying for the second node. But when quorum is lost, you have to perform a manual intervention in order to restore the state of etcd such that it can be writable. Therefore, having only 2 nodes it's a non-option. Then we have some other options involving external systems, but that defeats the purpose with edge. Just to be concise, it's also more complicated. So you could imagine like a third super small form factor device that would be physically located, co-located with the other 2 nodes, and in that sense, it could act as a tiebreaker, but it's also just additional complexity, additional cabling, and we opted to not use a witness. So what did we actually decide to do? Yeah, this is originally supposed to be Pedro and I. I think I was Frodo, and Pedro was Sam, but he's not here today. So yeah, we set out on this quest. I didn't quite catch that, but yeah, the goal here we're focusing on is stateless applications and the availability for those apps. So we're not, this is HA star or with a big asterisk. So in terms of like cap theorem, it's mostly highly available. And what that means is it's highly available for applications, assuming you've configured your apps in such a way that they are distributed across both nodes. The API server, like the control plane, is not strictly highly available. So it's sort of A with an asterisk, and then P because it survives network partitions. But it's not strongly consistent. It's eventually consistent, which we'll see. So yeah, it's kind of like AP star. That was our goal, and we hoped to make it as simple as possible. We'll see in a minute what that looks like. And we, like I said, we didn't want any external dependencies. We didn't want any witnesses or like an external database, because that just defeats the point with the cost savings. And then just to be totally clear, there's no conundrums here. We're not claiming to solve the cap theorem or anything, which I think I already touched on, but yeah. So how does it work? We have here a picture of a 2-node cluster under normal operation. So we use the terminology leader and follower to designate the relative roles of the two devices. And we use Kubebit to load balance between the two API servers. And we're also using K3s. And I know that, or most people here might know that K3s bundles all of these different components that I have shown here into a single binary. They're just split out for the purpose of illustration. But essentially what we have is this stack involving K3s, kine, postgres, and kairos running on each node. So we've switched out the backing store. We've switched out etcd for postgres. And then kine is a tool that allows us to do that. So kine is an etcd shim that sits between the API server and the backing store. So it's basically a gRPC interface that the API server talks to. And as far as the API server is concerned, it's talking to etcd, but really it's remapped into SQL queries that get executed against the Postgres database. So that's all running on the two nodes. And then sort of out of band, we've used our Go-based agent to configure logical replication between the two nodes. So the follower subscribes to the leader, and what that gets us is eventually consistent data replication between the two nodes. And we only ever commit writes to the leader, but then they get replicated to the follower. Basically, the follower is just syncing data, and you can talk to its API server, but any request that hits its API server then gets forwarded to kine, and kine is configured to talk to the Postgres endpoint on the other box. So ultimately, you're only ever sending writes to the leader database. And then our agent, what we have here, it's called the liveness agent. That is just like a proprietary Go program that's layered into these bootable OS images that we build using Kairos. So Kairos is the foundation to this whole thing, and it's really what made this possible. That's an open source project that it's a meta Linux distribution, and what it does is it builds these bootable OS images with a Linux distro of your choice. It supports a variety of distros. And then it also has some out-of-the-box capabilities for bootstrapping Kubernetes onto the nodes and managing the content of the operating system. And what it uses an AB partition. So basically when you build an image with Kairos, and then you would flash that onto some sort of like a USB stick, or you can do it virtualized, of course. But then what you would do is you would boot a box with this ISO that you've built with that Kairos image. And then during this installation phase, the actual physical device gets split into two partitions, and you would boot into partition A, and then you can basically use partition B for doing upgrades or fail back. So you could receive an upgrade over the wire as a container image, and then you write that image to the B partition. That other image would be another Kairos-based image that could potentially have a different version of Kubernetes included in it, or a different version of our agent. And then our agent would initiate basically a boot into the B partition, and then make the A partition the fallback. And if that anything in that process goes wrong, we automatically, stick with that. We boot back into the known good partition. And that's how we can perform all this configuration in a way that's entirely declarative. So it's all driven through Cloud init. We have Cloud config files that specify all of these different systemd services, which I'll touch on here in a second, but like our agent and kine and postgres and so on are all configured with systemd, but it's not imperative. It's all defined declaratively using this Cloud init configuration. So yeah, this is high level is how a 2-node cluster works. Then we want to talk about failover. So assume that maybe the leader node got unplugged or had some sort of catastrophic hardware failure. Then what we have is we have health checks that are continuously being executed by these two agents against one another. And that's configurable in terms of the interval at which the checks run. But the checks are basically just a ICMP ping, a TCP connection to the other host's API server, and a TCP connection to the kubevip endpoint. And we also support like a custom health check script. But the gist of this is basically, seeing is the other node okay, yes or no. And then we have a state machine that controls these transitions. So assuming the leader got unplugged, then the follower's liveness agent would determine that it needed to reconfigure the system. What that looks like is basically shutting off all of the Kubernetes components in order to reconfigure kine, because if we remember, kine was actually on the follower, kine was pointed to the leader's Postgres endpoint. So now we execute some SQL queries to reconfigure things within Postgres, and this is really minimal, and I'll explain in a second what I mean exactly. And we also reconfigure kine to point to local Postgres. But yeah, the SQL queries I'm referring to are just updating the underlying sequence on the Postgres database, because one caveat with logical replication is that it actually just replicates the data. It doesn't increment the sequence for the primary key column in the table. So we just have to figure out what's the highest ID and then update the sequence to reflect that. Otherwise, you get all sorts of corruption when you restart Postgres and kine. But yeah, now we end up in this situation, which is that we have only a single node, and it used to be the follower, but now it's the leader, and it's got its kine endpoint talking to the local Postgres, and we can just hang out in this situation for as long as necessary. But we have options. So what happens next is one of two things. Forgive the terrible Lord of the Rings jokes, but yeah, we might either replace the failed host entirely, which would be this situation here on the right, or on the left we could also imagine another scenario where the machine that went offline just gets plugged back in, like maybe someone pulled the cord and now they realized and plugged it back in. So we'll talk about that one first. So the original leader comes back, and then this initiates a process that we call demotion. So basically, this machine will boot back up, and then that state machine that I referred to basically performs some checks at boot to determine that it should no longer be the leader and that it should actually reconfigure itself. So basically, we have a one-shot systemd unit called the kine endpoint reconciler that runs on boot on these machines every time prior to allowing kine and K8s to start. And it just runs some initialization logic in addition to the liveness agent. Basically, what it'll do is it'll compare some data that's stored on disk against some information that it will receive through some RESTful API calls that it makes to the other host's liveness agent. Basically, each machine has a file on disk that records its state of the world in terms of like which machine is the leader, which is the follower, and like an last updated timestamp. So this endpoint reconciler will fetch that data from the other machine, and it will indicate that the other machine has promoted itself in the interim while this machine was offline. So then what this machine will do, the original leader that's now needing to be a follower, it will drop its subscription. Well, I guess I don't have the picture here, but it'll drop its subscription, it'll drop its database entirely, and then it will subscribe to the new leader and with a certain flag that copies data. So basically it resyncs from zero, and ultimately ends up then in an eventually consistent state through that logical replication process. Yeah, that's a demotion. And this is how we resolve network partitions. Because if you could also imagine, rather than the physical like power being pulled, you could also think that, what if there was just some network partition that manifested between the two nodes, then they would actually both promote themselves. And that the tie break is that timestamp. So whenever a state change occurs to the file that's on disk that the liveness agent is maintaining that represents the state of the world, it updates that timestamp. And there's inevitably going to be a newer timestamp on one of the two machines. So then assuming that network partition is remediated, they'll just cross-reference one another, and one of them will, like, quote unquote, win because it'll have the newer timestamp. And then that one will demote itself and do the dropping of the database in full resync. So now here is the logical replication I was referring to. Okay, so now the last scenario is host replacement. So imagine it, there was a catastrophic failure and we need to ship a new device out to the site. What we would do is just boot that device, and then it has access to information. So it would either get it from like a public SaaS endpoint that our software provides, or it could actually be baked into the machine through some configuration files that we reference when we're working in an air-gapped context. But basically, this new machine will know that it's part of a cluster with the other remaining machine, and it announces itself. So basically, we have this replacement machine, and we have this failed machine, and we have the one remaining machine. And this guy's going to boot up, and its agent is just going to say, "Hey, talk to me, not the other one." And then we're back into the same diagram we're all familiar with now, and operating normally. So those are the four sort of main operational modes of the system. And then lastly, regarding upgrades, we opted for a simple flow where we just pause everything. You could imagine a sort of a more complex solution where you swap the devices between being the follower and the leader and pausing them and unpausing them. And you would theoretically have no downtime if you did that, but it would require a minimum of 2 transitions back and forth, which involves copying the entire database, which is just risky and inefficient. So we've opted for this pause-based upgrade flow, where you basically just tell both machines to stop executing their health check against one another, and then we upgrade them at random because they're both considered control plane nodes. And we're actually using system upgrade controller under the hood with a control plan, with a plan that just targets the whole control plane pool. So they get upgraded, and then as soon as they are both back online, there's just some automation in place to start executing those health checks again. All right, now I have a little 5-minute pre-recorded demo. So let's see it. Here we have a 2-node cluster. We can see it's healthy. And I have this app deployed on it that is the Gamebox app, which is from Defense Unicorns. I don't know if anyone's ever seen it, but it's pretty sweet. It uses WASM to run all these old school games right in your browser. So I've deployed it in such a way, I'm just going to pause this for a second, that the app is running on both nodes. So that's the whole thing about app high availability. So the service that's exposed is going to route to an eligible pod running that application, regardless of whether we can actually commit rights to the API server. We can see here we have one with the TN1 prefix that is marked as the leader. So we have these annotations. We have a leader and a follower. They're both healthy. And we saw TN1 was the leader. And then there's a lot going on here, so I'll just pause it. But basically up in the top right, we have the logs for K3S And then below that, we have the logs for kine in the middle right. And then on the bottom right, I'm just every 1 or 2 seconds listing the nodes against the API server. And we'll see that go offline as the promotion happens. And then the top left is our agent. So it's logging some stuff related to health checks. And then the middle left is the PostgreSQL logs. And then we've got K9s on the bottom left. So things are just going happily along. They're both ready. Logs are scrolling. And we, I think, could see in the top left that the last health checks all passed. So this is virtualized. I just go into vCenter and power off the leader. So you can see that's TN1. That was the leader node. And we'll start to see some stuff change. The control plane endpoint health check failed. And the ICMP, the ping failed. But we have to exceed this threshold. So 4 health checks have to fail. And we see 3 failed, but now it'll wait another 30 seconds before checking again. So by default, if all checks fail, then the system will initiate a promotion after 60 seconds, basically. That can be tuned. And we can see here, I just switch back. The app's still working. So can play some more Mario while we wait. And now I think that 30 seconds has elapsed. So yeah, all right. It initiated the promotion. So this is the agent logs on the follower machine. I should have clarified that before. But I scroll up here so we can see it stops K3s, it stops kine, and then it does some stuff to the database. So it resets that sequence that I was mentioning, and then begins the process of rebooting everything. And this is actually what takes the most time. So we've benchmarked this a little bit, and it's usually 5.5 to 6 minutes before the control plane is operational again after a promotion. And the bulk of that is actually the time it takes to reboot kine, because I think it does some re-indexing during that reboot process against this new database, because it was previously talking to a different database, and that re-index process takes a little bit. And I actually cut the video here, so we see immediately things are booting back up again, but really there was sort of a 3-minute delay in the middle there. We can see K3s is running and kine is running, and we actually still see everything as ready in the bottom right, but that's just because the system hasn't yet recognized the fact that other control plane node really went offline. We'll see that in a second. I'll cut back over. And that's basically tied to certain flags that you can set for the controller manager. So there's intervals where the controller manager will perform health checks against the nodes. And then also another interval where it will decide to bounce pods on nodes that have been marked not ready. So that has been tuned a bit to be faster than normal, but we can see that time period elapsed, which I think I have tuned to about 20 seconds. So now that TN1 node is marked not ready, and that's reflected on the bottom right and on the bottom left. And we see some things happening, like the kubevip pod got bounced. And that's just something our agent does to accelerate the process of having the API server be routable. And we can see everything, everything's being bounced gradually to ensure that all the control plane components and whatever else should be running is all running on that one remaining node. So like the big thing to call out here is now we have writability, whereas if we were doing this with a 2-node etcd, we wouldn't have writability. And things are showing up as unknown, which goes away here in a second, but you can see, I'll just back up. You can see that the TN2 node now has that leader label, whereas previously it had the follower, and then it will become healthy here shortly. And then, yeah, more Mario. Just give it another few seconds. And now, yeah, that original follower has been marked unhealthy. And then our the underlying edge host doesn't go unhealthy in this video. This just takes a bit. There's some other timeouts involved there, but ultimately we can see that we have a new leader and we are in a functional state despite having shut off what was the original leader virtual machine. And yeah, more logs. I don't really think there's a lot here to call out. I think I will cut the demo there. Yeah, what do we have? Yeah, at the very end, we just see that it goes into a failed state. So just some more information there. But yeah, that is 2-node HA. And a couple more slides. Yeah, one interesting just Kubernetes configuration that I actually had my slides out of order. I should have showed this before the demo. At least that's what I meant to do. But you can use topology spread constraints to ensure that you have whatever apps that you need running on both nodes. That's sort of one of the caveats with this solution. So yeah, getting into that, what's left to do. A big one is persistent storage. One technology that we are actively exploring there is Longhorn, because it can do block storage replication with only 2 nodes. It's not the most efficient, but it does work. And then, yeah, there are other solutions out there, like etcd mirroring is one. And there's another cool open source project that we had initially explored quite extensively called Marmot. We ultimately switched over to Postgres for reasons related to FIPS compliance. Marmot under the hood is using NATS, and NATS at this time doesn't support FIPS. So there's some interesting alternatives out there where you could imagine, you know, how you would do this change data capture, because that's what the logical replication really is. That's sort of a higher level category for describing that eventually consistent data replication that's event driven. Yeah, and then this second bullet is really just a learning I had. I beat my head into the wall for longer than I would like to admit before figuring out that I had to do that, but we got there. So yeah, in terms of next steps, my colleague Nick Hall, I think, is in the room there, and I'm sure he'd love to talk to you. And also feel free to reach out to me directly. There's my email, and if you're interested, you could consider booking a demo. But yeah, thanks so much, and if you have any questions, happy to take them.
Any questions in the room right now? No? Okay, thanks so much, Tyler. That was great content. Look forward to mulling over that in my brain a little bit more, but looks cool. And for those of you that don't know, Max back here from Spectro Cloud is doing a raffle for a $100 Apple gift card. So he's got a sign up sheet back there. If you want to sign up and participate in that, feel free to do so. And with that being said, thanks again, Tyler. We'll move on to our next speaker, Lachlan. And just make sure you're muted on your laptop.
All right.
But do please turn on your camera if possible. So it gets captured in the Zoom, I think, maybe.
Yeah, good. Right. Okay, so I am gonna okay. Great. All right. I'm Lachlan Hayward. I'm a software engineer lead at Cosmonic. It says there, Dan and Eunice were originally going to be giving this talk. That's because they were supposed to be giving this talk, but we had a little change in the schedule. So what was theirs is now mine. They made this, I made this. We're going to be talking about resilient workloads in Kubernetes with WebAssembly native orchestration. So a little bit of an outline. What's the deal with WebAssembly and then WebAssembly components? What is WASM Cloud, CNCF project WASM Cloud, what does that enable you to do? And then how does that relate to Kubernetes? What are we doing with that? And how do we bring it all together? And then I'll have a demo at the end. Hopefully Tyler didn't anger the demo gods by failing to give them their sacrifice, their offering of a real demo. So mine is not going to get smited. So we'll see how that goes. It's always fun when we have the demo gods. Okay, so who has, you all just saw some WebAssembly with the browser stuff. Has anyone worked with WebAssembly directly? Yeah, obviously Liam has, yeah, you've done some WebAssembly stuff. What was the WebAssembly, what did you use it for?
Used to work for Disney and Disney Plus over WASM.
Yeah, awesome. Anyone else have any experience? That's in browser, right?
Yeah, in browser.
And on the edge.
And on the edge?
Yeah, I did a blog about it.
So WebAssembly came out of this need for running more optimized languages in the browser. And technically it's neither web or assembly anymore. You can actually run WebAssembly outside of the browser. There is a couple of different runtimes that you can actually execute WASM modules on. It is an open W3C standard, and it's pretty well widely adopted. Like Derek said, he was using it at Disney. Amazon Prime Video is using it. It's used on Cloudflare workers support WASM workloads. It's basically, you probably used it and you don't know about it. Figma, the design app, uses it in their browser app, and there's a bunch of other companies that are using it. But it is a safe and secure sandbox. It is sandboxed, which is only given capabilities when requested. So you have to say that this particular module is going to run with these permissions for it to actually be able to use those. It's efficient and small. It's polyglot, as in it does not need to be compiled to a specific architecture. As with the browser is not any particular, you don't know what what architecture the customer's browser is going to be running, right? So browsers can be running on any architecture, which means that the WASM workloads need to also be device or agnostic to the architecture that they're running on. And it is also, because of that portability, it's also, you can run it on the browser, but you can also run it on any device that is able to run that WASM runtime. It's kind of like a tiny VM. You can compile your code, and instead of putting it into a container or VM, you're putting it into this WASM module, and then that WASM module is what is then executed on the runtime. And again, architecture agnostic. WebAssembly you can think of as sort of a next evolution on like how you build applications. Sort of a little diagram here, but how do you share a CPU? Use a VM. How do you share a data center? Use containers. How do you share the orchestrator? You use Kubernetes. And how do you share libraries and application pieces? Is with WebAssembly components. This is a new piece. WebAssembly is one part. Now there's also WebAssembly components. If anyone has any questions, feel free to interrupt. It'll give me a chance to breathe a little bit. So WebAssembly components, you can sort of think of as a way to make utilizing WASM modules a little bit easier. WASM as a functional like piece of code only really takes numbers in and numbers out. It's basically numbers in a trench code. You can't do much with like arrays or strings or any sort of like specific types, which can make it a little bit difficult. And it sort of meant that everyone who was using WebAssembly was using their own sort of way of getting these types in and then back out when they actually need to execute WASM. So that's where WebAssembly components come into play. WebAssembly components are language interoperable. You can see here that we've got a Rust component and a Go component, but they're actually going to operate together. They do that through these strictly defined interfaces. You say that component A needs to be able to import feature X, and then component B will then say, well, okay, well, I'm going to consume that particular interface.
You said questions are good, right?
Yeah.
Do they get compiled together and like executable?
Yeah. So there's a couple different pieces, but effectively, yes. It's called composing that component into a single unified component.
Cool.
Yeah.
They still have their own separate memory. Yeah, no, WebAssembly is a stack-based virtual machine. So when you compose two components, you can, you're putting them together, but in the next diagram, you still have all the advantages of separate memory space. What's amazing here is that when you typically want to do this today, you do it all the time through REST or gRPC. You think milliseconds. I set up 2 servers. This is in the same process is where this happens. So it's lightning fast.
Yeah, exactly. So that interface is defined through a language called WIT, which is WebAssembly Interface Types, and specifically built for this purpose of being able to define an interface that one component can export and the other can import. And that is its own IDL, think Tradeoffs, but specifically for this purpose. So yes, this is exactly it. You take those two components, you compose them together, and then you get a single component C, which is that shared component. But you still get all the benefits of WebAssembly's core functionality, which is stuff like shared nothing linking, meaning that each module has its own not shared memory. It's all isolated, which means that there's no sort of cross-boundary. You can't try and reach out and access a piece of memory. It will fail. It will crash the application. So if you happen to have something that's insecure, maybe it's a custom or a customer component that you want to run within your ecosystem, then you can do that without exposing the internals of your system and the memory that's allocated to that. So that's beneficial for running customer workloads or plugins or things that are untrusted. It's useful in that instance. But yeah, as Liam said, it's not happening across the network, it's happening in process. So it's nanoseconds as opposed to milliseconds. So let's take a look at what a component code looks like. There is 2 ways to read WebAssembly. There's the compiled sort of binary format, but then there's also this WAT format, W-A-T. I don't know what that stands for, but that's what it looks like. That's the code of what that component code looks like. You can see here at the top, we've got some imports. So this is importing some sort of logging piece. Maybe that makes use of some other logging component. In the middle here, this is the core WASM module. So this is the piece that we're able to, that's the part that's currently using in the browser. That's WebAssembly modules. And then down the bottom here, we've got the export, which is the run. This is what allows the host to actually execute that particular component. So it's, as you can see in this middle section here, there's no sort of, all the types that are in there, they're all integers, right? Whereas out here, we've got actual strings. And it's sort of, you're able to use a little bit more useful, helpful types to write applications. So what do WASM components do for me? This might trigger a couple of people, but do you want to talk about log4j? Probably not. So what if, rather than having to go and patch every single application, they use log4j, you were able to just swap out that piece of that component at runtime rather than having to recompile everything for every single architecture that it needs to run on. Just flip that little component out because like that's what it looks like. The code is pretty easy to compose back together. It's like just adding some text together effectively. You can save time through contract portability, means that one team could develop a contract for a particular feature, and then any other team can make use of that feature in any other language that they want to. So if you've got a Rust team who's running something a little bit more performant, and then you've got a Go team who's running something else and they need to make use of the similar sort of functionality, you can do that because it's through this specifically defined interface. Money, obviously, the time and money it takes to develop stuff, you can move things around quicker, but also with WebAssembly modules and WebAssembly components, there's no cold start. It executes it as it needs to. You can then therefore scale to zero. There is no long running components. It's either executed or it's not. You can optimize your ops, which is this log4j situation, and then again that being able to write pluggable capabilities that you can deploy across teams and be able to like swap out functionality without having to re-trigger pipelines and stuff like that. You can just swap it out at runtime. Okay, so how do we actually deploy any of this? This is where WASM Cloud comes into the picture. WASM Cloud is it combines those benefits of WebAssembly components with the benefits of a control plane. So we're able to deploy these workloads wherever they need to be. It's WASM native orchestration. So you can see here we've got the ability to deploy WASM Cloud hosts within different Kubernetes clusters across edge devices, constrained edge devices, or even in client browsers. It doesn't matter the architecture again, you compile it once and it can run wherever it needs to, which makes for moving workloads pretty interesting as well, because you could have a component that's compiled once to run in an edge location, and if you find it's better to actually push it closer towards the customer, you don't need to recompile it specifically for that one, it just moves closer to the customer. So this is more of a better together sort of story. We can utilize Kubernetes and run WASM Cloud hosts within those Kubernetes clusters, and that's what this demo is going to be about. Let's see what it's going to be. So this is kind of close to what we want. I didn't get a chance to update these diagrams a little bit, so you can forget about the edge node. I'm just going to have two Kubernetes clusters. They're running in GKE. One of them is running in US West, and one of them is running in US East. And we have WASM Cloud hosts running in either. What I should be able to do, where the demo gods allow me to do such a thing, is to kill off one of these regions. For some reason it dies, the power goes out, and someone kicked a power cord or something in the data center. And then what it should do is it should fail over to that other region. So we should see the traffic pull across. What I have is a little demo application, which is this guy right here. You can see at the moment it's hitting, well, we're in the east, so that's where it's hitting. But we've got some counts here. Every time it takes a hit, it will increment some of the data. So it's going to hit the regions there. You can see it's actually pulling across both regions there. So it's actually managing that traffic and pulling it across to see where that workload is executing. So this is what it looks like inside of that WASM Cloud host. We have an incoming HTTP request. We have that HTTP server that is a provider, and that's providing one of those interfaces to this hello actor. That's another component that lives within that system that's consuming that export. So that's that interface that we were talking about, is those two pieces are talking together. And then the actor, the hello actor and the metadata provider, those are another two pieces that have their own imports and exports. So this particular demo is running in GKE, and that metadata is basically pulling data off of the node that it's running on to be able to say like where it is, all that sort of stuff. We've actually got another demo of this same thing that runs in Fly, in fly.io. And the metadata provider there, obviously it's not the same data. You have to get different regions, all that sort of thing. So that metadata provider, when it's running in Fly, it swaps out for the one that's relevant to that particular host. So what we should see is, that host is going to go down, and then we should still get traffic across to the other region. So here we go. We have, the way that this works alongside of Kubernetes is we have our WASM Cloud operator, which allows you to deploy CIDs that sort of define that application and pull across into the Kubernetes that deploys those hosts within the clusters. So this is our dashboard. You can see the demo is running here. There's those components. So we've got the GCP metadata provider. Key value is how it's storing that. Actually, it's kind of a little more advanced than this one in that it actually stores that data in a Redis connection. I think it might be, what's the open Redis one now called? Well,
Valky.
Valky, that's the one. So it's running, I mean, it says it here somewhere. Yeah, there it is. Valky. So these are the two WASM Cloud hosts that we've got. One is, oh, we didn't have the tag on that one. This one's the US West one, and this is the US East one. You can see this one's been running for a little bit longer. Over on the left here, these are those, you can sort of think about those components as composable Lego blocks. So when it runs, it sort of snaps those pieces together, and then it will redeploy that application where it needs. You can see over here, we've got some components running on each one. This is sort of like max instances it can run, so it's sort of like, like the maxed instances of that particular component that host is allowed to run given the resources of that host and that sort of thing. And then these providers are like the components, but they provide that interface. So, GCP, metadata provider, key value Redis provider, HTTP provider, and then there's this Cloud Hello component that's sort of making use of all of those interfaces. So now what I should be able to do is delete that config, which is what that CID comes from. And we should see, yep, there it goes. There goes that host. That is still the one that's running in US East, but I can still go to the application and the US West C is the one that's not. Oh, yep, there it is. Okay, so it is still running. Yeah, cool. So far so good. Now the next thing that should happen is when I reapply that that config. There it is. We should see that host start back up thanks to the WASM Cloud operator that's running in that cluster there. And then we should see some of these components. Yep, there it is. Now the application's reconciling because it's recognized there's another host that's running, and it's going to try and make use of that host based on the configuration for that application. So I'll come back to that in a second. But yep, there it goes. So there's 1 of 50. It's got 2 of 2 running. It should pop up with a third in a second. We'll see.
There's only 2 on that one, Mark.
Oh, there's only 2 anyway.
So now, if that version that was running received an update and a new version got deployed, when it reconciles, will that other node automatically pick up the new version?
Yeah, so that's controlled through the, actually I can show it here. It's all built around these manifests. Oops, come back, please. So if we're, I mean, you all definitely know YAML at this point, but same deal. It's built around this particular manifest, which is based on the OEM spec, and we try and do as much as we can with open standards, because we don't want to be rug pulled, we don't want to be Redist or anything like that. So we've made that stance that we're going to do as much as we can in the open source, which is why Cosmonic donated the WASM Cloud project to the CNCF, and hopefully in the next short period, TM, we will go from we'll become an incubating project. So we submitted the proposal, now we're just waiting to see what's next. Okay, so as part of the spec, we have the hello component. It's coming from this image, and that image is it's part of an OCI registry, but it's not a container. It's actually the WASM workload. Same deal though, we're using these open standards to sort of make sure that it works with as much of the ecosystem as possible. It's using this daemon scaler trait. It has to run in GCP. It should run 50 instances. We're linking that particular component to this key value. We're linking it, these are the features of that key value it should use. This is where that Valkey instance is running. It's linked to the metadata provider, and these are those import exports, right? So we're linking those import exports together so that it knows how to actually make use of that. And if we wanted to change that version, all that we would do is change what the deployed version of it is and redeploy this manifest, and then the orchestrator would take care of that. It would basically stop that component running on whatever host it is, and then download the correct version of the new version of the component, and then deploy it onto those hosts.
So for like a user who was on your website that was interacting with these components, it would be seamless to them. They wouldn't notice anything.
Ideally, yeah. So these workloads all running in the server. I mean, yeah, the next time they refresh the page or whatever, they will get the next request that comes from the new version of the application. Yeah.
So I just want to, maybe I'm hearing you differently different times or something like that. Because sometimes I feel like you're doing some kind of interesting like Erlang, like hot swap in a running process, swapping one component out for another one. But that's what you're doing?
Yeah.
That's kind of crazy.
So yeah, if I wanted to, I have not got that plan, but we could theoretically, all I would need to do is change that version there and redeploy it. It doesn't need to recompile the component or anything. It's just swapping that out at runtime, which means that if you had
the same process still.
It is. Well, so we do a little bit of magic around that import export piece. We use the WRPC protocol, which is sort of that way that we're communicating in memory to make that happen. But it's built on the WASM time runtime. Liam may be able to talk to this a little bit better.
Think about when you build a regular app today, like with Java Spring Boot or any Golang framework. You pull all the libraries into a single binary. So you have database drivers, you have your log drivers, you've got maybe OpenTelemetry, whatever. What WIT does is you stop programming to specific interfaces. You can still program to a specific interface. We actually just released for a Fortune 100 bank a Postgres driver in this standard, which obviously only works with Postgres. Postgres is not a great, databases are not a great example, because when you're designing these abstractions, you kind of sometimes go to the lowest common denominator. But most key value stores are pretty much like each other. So there is a WASI KV. So instead of pulling Redis or Valkey or Couchbase into your application is very small and it just has your business logic, and it says, I need a WASI KV, I need a WASI logging, I need a WASI HTTP. And then at runtime, the host can provide those particular components. Actually, the provision can come from 4 different places in WASM Cloud. A component can satisfy an import, so you can have one component, one Lego block, fill another one, if it matches contracts. It's like the Lego blocks, two like things go together. The host itself can provide the contracts. WASM Cloud, I think, is growing so quickly because it's extendable at runtime with machine native code. So let's say you have your own custom thing. You want to make an LLM Lego block. Somebody made actually an LLM Lego block. You can actually inject that at runtime through machine native process. So we have people that have created like IO drivers or sensitive data or other sorts of standards that they want outside of the secure audited WASM Cloud host runtime. And then the fourth way is that WASM Cloud also supports this WIT-to-WIT communication protocol. It's like gRPC, but for WIT called WRPC. And that lets you, instead of taking your business logic, serializing it to gRPC, setting up protobuf, serializing gRPC, and then talking and then deserializing back, you can just talk interface directly to interface. It's lightning fast.
It's crazy.
It is crazy.
Within process, and you swap it out within process.
Yes,
You swap out
yeah.
the versions with Lego.
Yeah, you just spin up at runtime. That every invocation is a new clean execution of WebAssembly. That's the way it runs. So there is, so when we're building these applications inside of the WebAssembly sandbox, you get all of these other amazing things for free. If you pull up the module again, go back to your slides, the WebAssembly module is self-describing. So inside of the module itself, it says, here are my inputs, here are my outputs. So you can create things like data schemas, registries. You know how to configure it sandbox even before you start it. So every WebAssembly sandbox only runs with the exact security configuration that it needs. Imagine if your apps, you instead of starting with all 534 system calls, POSIX, you could just start with access to just this one file or just this one network call. That's what you get in WebAssembly out of the box for free. So there's a ton of these derived benefits from this contract-driven development that's happening there underneath the hood. WebAssembly itself is not interesting as technology. What's interesting is when you adopt WebAssembly, what it means to how you work with technology. It's all these things that you don't have to do anymore, like the endless cycle of patching your app, right? You can just move it to the platform constraints.
Some of those other things, like with that glue piece of the imports and exports, it also means that we can have components that are running specifically on the device that provides some sort of dedicated access to a sensor data or like a LLM, for example, and you have the HTTP component running in a cloud node. It will come in, it'll make the request, and then it'll, depending on where it is, it might hit a slower running but closer to the user LLM model. And then if possible, it passes it on to the beefier cloud one. Because it's using that same contract, you can do that connectivity both in the host itself at runtime, but then also across the network as well. So you could have a component running in the local one, but then also do that across to a cloud instance as well.
Because these are, said in a different way, because these are self-describing, you no longer need service mesh, right? You have service mesh because containers show up with these black boxes. You have to say, well, where do I find this particular route in my network? And you send it to the service mesh, and it has a registry, and it will look it up and will say, oh, on this Kubernetes cluster over here in this pod, and deliver it. WASM Cloud gives you location transparency, and because when you start the module, you know exactly what it imports and what it exports, so you can automatically do these load balancing. By default, we load balance to local capabilities first. It's faster, inside the process, and then it's the next closest. And we do that actually underneath the hood with NATs. You can set up geozones. There's all kinds of neat things you can do for how you route like service mesh. But it's a much finer grained abstraction here with WebAssembly, but it's also described in a finer grained way. Just as when we had containers, virtual machine concepts like OpenStack didn't really apply. You could always inject like the concept of a machine back into a virtual machine days, and WASM Cloud injects its mesh into service mesh through the orchestrator. So everything just shows up and it works, but it's harder to go forward because it's not the same fine-grained abstraction. So all the HTTP endpoints that WASM Cloud publishes in the operator automatically get picked up by Istio or Envoy. It's just compatible with. but it's not dependent upon.
Which means that if there's a super constrained device that needs like 100 megs of memory, like it can do that because you're only running the WASM Cloud host. I think last count, the host itself was like 34 megs or something like that, and didn't actually need that much memory. A large WebAssembly module component rather is like in the megabytes. Yeah, most are like kilobytes. So it's extremely portable, low footprint size. Like there's a lot of benefits to WebAssembly and components.
What does this mean though for the client in the browser? If everything's running in the browser, how does memory utilization change there?
Yeah, so we have a host that runs in the browser. It's not updated to the most recent version of WASM Cloud. We just have not seen as much traction with that. It is something that we'd love to be able to get to that point, to be able to say, like, if the customer has enough memory to be able to allocate, like, run workloads on their machine, then we can sort of push that NATS network out to their browser, then that'd be fantastic. To make use of, like, customer CPU and not have to run it in cloud workloads, that'd be great. And it's theoretically possible. You just need creds for the NATS connection, and then that's because NATS is how it communicates. But this is typically like running those WebAssembly modules on servers and pods and stuff like that in clusters and that.
Just go to the URL on your Chrome. You're running Arc. You're too cool for me. Open up Chrome like a regular browser, please. And while you do that, the Zoom and Google actually just did a talk about WebAssembly. All of their new Gemini AI stuff for the browser for Android, it's all compiling down to WebAssembly. So you're using WebAssembly daily, but if you can open up Chrome for me, I don't know how to do it in Arc. I'm just not that cool. But if you just click on the URL bar, I want to pull something up. I want you to pull up the site settings bar here.
Are you looking at like developer tools or something like that?
I don't know, just like a simple, I'm going to talk a little bit about capabilities in the browser and make an analogy to WIT and what we're talking about, because I think we're circling on an idea here that is very powerful, but I don't think we've really communicated. Just open up CNN, anything. CNN, no, don't go to CNN, that's going to be a shit show right now. go to the most innocuous, neutral website of all time. PBS, oh God, no.
You're not hitting any wins here.
I don't know, GitHub, great. Now click just to the left of GitHub, click the little down arrow, and then go to site settings. Okay. There's this big idea right now that everybody's adopting, but nobody's really talking about, called capability-driven security, right? And it's the idea that like when you install something on a modern OS X or on your phone, it says, oh, this device wants to use this file, or my speaker, or my microphone, or my camera. And you say yes, and you're going to really fine-grained controls. In containers, you land on what? POSIX, right? The system calls, 534 system calls. And yes, there are ways to go back and lock those down. Docker by default shuts off the big 30. But if you pull up that list again, your browser publishes here a list of capabilities for every web page, right? Can I use your microphone? Think of those as WIT contracts. And the WIT contracts that you're programming around in an application sense are just like cloud endpoints, like KV or SQL or HTTP, the building blocks of modern applications. When I was at Capital One, we had 5,000 apps, and it was a big frequency analysis, and almost 2 standard deviations of apps were built out of 10 things. There was a blob store, S3, something like that, HTTP, logging, a very, very small list of very common things. And that was what we were thinking when we were like, oh, if we just have a small number of building blocks for our apps, we'd get there. And what WebAssembly is doing then is that because your application describes the building blocks it uses, you're locked into that sandbox by default. So even if there's some sort of a breakout, you don't have access to any other capabilities to move outside of your breakout. And that is a big idea. Somebody needs to do a blog post about, like capability-driven security is something that the water is boiling and we're all the frogs because nobody really talks about it. And WebAssembly is I think the way that will embrace this in our applications.
So if I'm understanding the way it runs, you're talking about it runs like a script, it just runs through and then completes. There's no long-term running process. does that mean that my applications need to be stateless? Or if I want to do something like polling, for example?
So state is, essentially injected through the runtime into an outside capability. So state is not held inside of the WebAssembly module. The WebAssembly module itself is stateless, but it still connects to, Redis or some other KV store or to a SQL database. We can do long-running WebAssembly, and there is a company out there that's done a framework around event-driven WebAssembly. So I think there's many different strategies there to think about that. But these are not stateless apps. Even though WebAssembly is stateless, the capabilities that you attach to your WebAssembly app are not stateless. These are
Database provider or
yeah,
whatever.
WASM Cloud supports microservices and event sourcing and all the other common application paradigms that you see in modern enterprises. And we have referenced apps in our examples repo.
That makes sense, but if I'm writing in a modern language, it makes it really easy for me to store a lot of state, right? Does that mean I'm kind of working against it if I, just say, take in something from a request and store it in a map? Like, does the next run, it just assumes that the application runs fresh on every single request?
The application is running fresh on each request. So there is some design that goes here. I think it's a difference between, and let me take a step back. What we have not released, but we're about to release is idiomatic tooling for Go. So you can take a regular, Go app and you compile the entire STL right down to WASI. Now that would sometimes have some weird effects because everything runs to completion and it may not perform exactly like what you think it would. It's not reentrant would be maybe the terminology that we might use in an application construct. So I think that there is some re-architecture here to be WASM native, just like there was some re-architecture or rethinking to think about how do we really be cloud native. I think about the challenge of really doing stateful containers. I think is a similar idea to these stateful apps. In WASM native programming, you're more relying on KV or other sorts of elastic things. I do think there is and there will be some interesting developments around long-running WebAssembly. One of our lead infrastructure engineer, Dan, spiked on it and wrote a framework for long-running WebAssembly, which would be more of a re-entrantless approach, like what you're talking about. But right now, the sort of paradigm has evolved around, taking huge advantage of WebAssembly's chief properties are it's so fast that there's essentially no cold start penalty. The WebAssembly starts in microseconds, around 50 to 100. So network requests are measured in milliseconds. So you can invoke for every request. This is how Cloudflare, Fastly, and Akamai give you, your edge compute, and just charge you per compute. And they actually give you it's underneath the hood. It's all WebAssembly. They use a different engine. One of them uses V8, which is headless Chrome. Another uses the same engine we use, which is WASM time. And I'm not sure what the third one uses. They haven't told us. Did I answer your question?
Yeah, absolutely.
Yeah, I tried to give you the complete answer.
Makes sense. Just to touch on the last point, you said 50 to 100 milliseconds to start?
Microseconds.
Microseconds. Okay.
A thousandth of a milliseconds, so 50 of those. And so that's how you could have sub-milliseconds, execution time for your WebAssembly. When you've composed two applications together, that boundary is crossed in nanoseconds. Yet another 1,000th of a microsecond. So it's pretty lightning fast when you're talking about this, how, if I move to building my applications out of building blocks versus how I do it today, it's nothing compared to, the network speed. It's an order, your orders of magnitude less.
Thanks.
Thank you for a great question.
Can we dig into just a web server a little bit?
Sure.
So web server, I came from Rails, which is nuts. I'm going to Go and I'm like, sweet, I can just pump up Go routines and I'm super happy.
Yeah.
But it seems like this is saying there's nothing running. I'm just gonna suddenly start hitting it. Microseconds later, I'm serving a request. And it seems like it's gonna scale wide really quickly and easily to Is that something y'all will do? If I'm gonna say, go from 0 to 10,000, is that?
Yeah, 10,000 will run on my MacBook. I mean, when these compile down, it depends on the language you use. It depends on the language. Interpreted languages right now bring the interpreter into each and every module because they're all share nothing. We're working on this year a share some things proposal, which will let you load, say, the Go interpreter or the C# interpreter once. That's a much larger example, and then just have your business code for each scale. So that will be much more efficient when we land that. But even now, those are still pretty small. I think the C# ones we just built last week were like 5 meg per instance, which is pretty small compared to if you think about a C# container. I've never seen a 5 meg C# container before, right? And now each one of those scales vertically, but on a single node, you're operating tens of thousands of these WASM instances.
Yeah, so I'm thinking about like one request per WASM instance, but I think about lots of WASM instances per.
That's right.
utility.
Yeah, the web servers themselves are separate and actually machine native code that is running inside of the host. So the web server is not inside of WebAssembly. So there's this piece of what are you running in the sandbox? You know, as a platform operator, I don't trust anybody, especially not my own developers. So I want to run all of their code in the platform. So when we help orgs roll this out for their platforms, they typically will create like a sidecar, like, hey, here's your my bank or my company functions that all developers get as a part of your standard golden template out of Backstage, right? And then you just add your business logic, and then actually we compose those together in WebAssembly. So the WebAssembly module then its little Lego block only needs HTTP at runtime. We satisfy all the other capabilities. Now what happens when there's a bug? No developer ever has to patch it because the developer just wrote look up customer ID out of database and update their points to 10,000, whatever, like.
Developer roles gets pretty small to like
Right.
just write the SQL and response or whatever.
Think of, Lachlan made the analogy earlier around these epics of tech on your handout here. Think about what you've left behind in every epic. When you moved from virtual machines, you left behind all the hardware. You moved to the data center, to the public cloud, you left behind the data center. You moved to the container, you left behind the operating system and all that code. You move to Kubernetes, you're just bringing in your piece of orchestration, your pod configuration, right? Your Helm chart, right? Per app. And now what we're saying is, well, why not leave behind all these common libraries as well?
Yeah. It's pretty transformative.
It's a big idea.
Yeah, when Liam talks about like we're landing all this stuff, we have a number of developers like Bailey Hayes, our CTO, is part of the Bytecode Alliance, who's building and designing the standards that are going into these technologies. So WASI is the WebAssembly standards interface. I forget which one it is, but that's backed by the Bytecode Alliance, which is not just us, it's a bunch of other companies who are contributing to these standards.
AWS, it's Siemens, Sony, it's all the big org. Microsoft is huge in on this. Microsoft's .NET 9 has full support for, .NET 8 has full support for WASI 1, and .NET 9 has full support for WASI 0.2, which is this WebAssembly component thing that we're talking about. Microsoft has been an awesome partner. This already, if you're on Azure now, every Kubernetes node you spin up runs this by default, by the way. So it's already there. VS Code just announced their new plugin models, the WebAssembly component. So it's sort of like creeped in and taken over everywhere. And what we view WASM Cloud as WASM Cloud is sort of like, it's the pick and shovel that regular developers use to get this bootstrap in their org.
The VS Code one's interesting because it uses it, and they've just done a sort of a proof of concept at the moment, but they're looking to build it out as the contracts become more available. But it's basically like, as a plugin developer, you have access to all the capabilities that are part of the VS Code interface, right? So as a plugin developer, you can say, oh, well, I want to use this big particular piece of that plugin functionality, and then all the code that you run as a plugin developer is untrusted by VS Code, but gives you access to things like, I don't know, changing the campus, or like adding in a language server, or all this other stuff through that contract. So it's interesting for stuff like that. Yeah. Any other questions? Awesome.
Great questions.
Yeah, awesome. Great discussion. I appreciate it. Well, thanks very much. That's
All
us.
right.
Oh, I guess I'll do the whole end of slide share of, this is where you catch us. I'll get that slide up right towards the end. Can't tell fast enough. There it is. Okay, so Cosmonic is our company. We're pushing for the WASM cloud community. So there's a QR code there for our Slack community. The code there is for, I believe, our GitHub. Appreciate stars. That's what boosts us up there, get us onto that trending page. So if you can go and give us a star, and yeah, hit us up in the Slack or come talk to us afterwards. Appreciate it. Thanks again.
All right, that wraps up all of the normal content we have. We'll be hanging around a little bit for some social time. Feel free to hit people up if you have any further questions, or hit me up and I can get your questions forwarded to the right person. Thanks again, Tyler and Lachlan, for coming and speaking with our community. And don't forget, there's the raffle over here for the Apple gift card. Thanks again to SpeedScale, Georgia Tech ATDC, Calendly, and Spectro Cloud for sponsoring all the different various parts of the Meetup event. Again, my name is Joe Searcy. I'm the host of the event here. If you have any ideas or recommendations for future topics or speakers, please hit me up. Would love to cater the content directly to what you guys want to hear. So thanks again for coming out. Everybody on the phone, we'll see you later.
Thanks, Joe.